Now, I've already made a couple of videos about work, which you can view in the card above, and I explained that the work done on an object is equal to the force applied to the object multiplied by the distance the object travels under the influence of this force, multiplied by cosine theta. And theta is the angle that the force is being applied to the object relative to the direction of its motion. But what I didn't discuss is how we can calculate the work done on an object when the force varies over this distance or varies over time. And in most real-world situations, this force will vary. So imagine we have a particle being displaced along the x-axis under the action of a force that varies with the object's position. And I've drawn a little diagram here where the initial position is x sub I, and its final position will be x sub f, and we've got our force vector here. If we want to calculate the work done on this particle, we can no longer use our previous equation, work is equal to the force multiplied by the distance, multiplied by cosine theta. And this is because this formula assumes that the force on the particle is constant over the distance. But in our situation, the force is no longer constant. But let's say that the force varies with position according to this graph here, where we have the force on the particle represented on the y-axis, and on the x-axis is the distance the particle is moving. From the particle's initial position, x sub I, the force starts to increase and peaks about halfway between x sub I and the final position, but then it gradually decreases. So if we cannot use this formula to solve the equation or to find the work being supplied to this particle, then what do? So we can break up the motion of this particle into many small displacements, and we can represent each of these displacements as thin rectangles or bars on this graph. So you notice that the top of these bars are horizontal, which means that for each of these displacements, we're assuming that the force is constant. Now, it's not exactly constant, but it's a good approximation. So for each of these minute displacements, we can say that the force on the particle is constant. When the force is constant for one of these displacements here, then we can approximate the work done by the force, as the work done is approximate to the force at this position along the x-axis multiplied by the minute distance that this particle is travelling in this instant. And this is just the area of the shaded rectangle on our graph here. If we imagine now that the force versus the x-curve is divided into many of these intervals here, into many of these bars or rectangles, the total work done for the displacement from the start position to the final position is approximately equal to the sum of all these terms. So all we're doing here is creating many different rectangular approximations and fitting them underneath this curve here, and then adding up all their areas to get an approximate area for the area under the curve. So the force at the beginning could be around 10 newtons, and we're moving a distance of a millimetre. At the start of the second millimetre, maybe the force has gone up to 10.1 newtons, and so on. And we add all these elements together. But doing this in this way doesn't really get us anywhere, unless the size of these bars, or delta x, is allowed to approach zero. When they approach zero, the number of terms in our sum increases without limit. But the sum does not give us the true area under this curve on our graph. This leads us to a section of mathematics called integration. So the limit, as delta x approaches zero, for the sum of the areas of the small displacements can be written with the definite integral, with the lower limit being x sub I, the start position, and the upper limit being x sub f, the final position, of the formula for the continuous force on our particle multiplied by delta x. And this delta x represents the infinitesimal distance that the particle is moving at each summation. And our f sub x term here could have any continuous equation that we like. So for example, it could be negative x squared plus 2, for example, which will produce a curve on our force versus displacement graph. And then what we'll need to do with this equation is integrate with respect to x. So if our force on the particle varies with displacement, the work done can be found with this definite integral. So how can we use this to solve physics problems related to work? Well, I'm going to go through two different types of problem here. The first question, we have an interplanetary probe attracted to the Sun by a force given by this equation here. So the force is equal to negative 1.3 times 10 to the power 22 divided by x squared, where x is the Sun probe distance measured in meters. So our probe starts off at the Earth's orbit and it's slowly moving towards Mars. So using integration, we need to determine how much work is done by the Sun on the probe as the probe moves away from the Sun. So our start position, x sub I, is 1.5 times 10 to the 11 meters. So that's 150 million kilometers, and that's the Earth-Sun distance. And its final position will be 2.3 times 10 to the 11 meters, or 230 million kilometers. So the average distance from the Sun to Mars. Now, before we solve this problem, do you think the work done on the probe by the Sun will be positive or negative in this case? And if you're not sure about the answer, try and think back to the work kinetic energy theorem, where work on a particle or on an object is equal to the change in kinetic energy of that object. So if you think our probe, when it's close to the Earth, the probe is moving relatively fast, orbiting the Sun along with the Earth. But as it moves out towards Mars's orbit, it's going to slow down because the Sun is doing work on the probe. It's taking away kinetic energy from the probe and slowing it down. So the Sun's gravitational force is working in the opposite direction to the probe's motion. And if we draw just a quick diagram here of a box or a square, and the square is moving towards the right of the screen, so it's moving in the positive x direction, but imagine the Sun is pulling it back with a force in the opposite direction. When it's doing that, then if the box is in motion, if it's moving with a certain velocity forward, but then its velocity is going to slow down over time. So as a result, the work done on the probe will also be negative. Work is being taken away from the probe and it will start to slow down. So let's write out our integral of the work done when the force varies over distance and substitute in our force equation into this integral here. So we can remove the negative 1.3 times 10 to the power 22 because it's a constant and we're only integrating with respect to x. This leaves us with x to the negative 2 or to the power of negative 2. Now we can use something called the power rule in integration to solve this type of problem. And the power rule can be summarized with this equation here. So the integral of x to the power of n dx is equal to x to the power of n plus 1 divided by n plus 1 plus a constant c. Now when we have a definite integral, this constant gets cancelled out. But when we integrate x to the power of negative 2, we add 1 to the power, so it becomes x to the minus 1, and then we divide it by minus 2 plus 1. And we end up with negative 1 divided by x. And we place this in square brackets here. with the lower limit and the upper limit. And we're integrating between these two values here, 1.5 times 10 to the 11 and 2.3 times 10 to the 11. And we substitute these values into the value of x here. So it would be -1 divided by the upper limit, 2.3 times 10 to the 11, minus the lower limit of 1.5 times 10 to the 11. So -1 divided by 1.5 times 10 to the 11. We always subtract the lower limit from the upper limit. And when we sum this all together, we get -3.0 times 10 to the 10 joules. And this is how much kinetic energy is being taken away from the probe as it moves from the Earth's orbit to Mars's orbit. So we have a negative work value here, and it tells us that 30 billion joules of kinetic energy is being taken away from the probe as it moves from the Earth's orbit to Mars's orbit. This means that the probe's velocity will decrease as it approaches Mars. So let's do another problem. We have a 100-gram projectile, and it's fired from a rifle having a barrel of 0.600 meters. Assuming the origin is placed where the projectile begins to move, the force exerted by the expanding gas on this projectile is given by this equation. So the force is equal to 15,000 plus 10,000x minus 25,000x squared. So it's a polynomial equation. The force is in newtons and x is measured in meters. So now we need to determine the work done by the gas on this projectile as it travels the length of the barrel. So x sub I, our initial position, we can set at 0 meters. And our final position, x sub f, we're going to set at 0.600 meters, right at the end of the barrel. And I've written out our force equation here. So we've got our integral here for the work done, and we can substitute in our force equation now, our polynomial equation. And again, we can use the power rule here for each term in our polynomial equation. And again, the constant term will get cancelled out when we have a definite integral. And a definite integral is where we are measuring the area under a curve from an initial position along the x-axis to a final position along the x-axis. So 15,000 becomes 15,000 multiplied by x. Our second term, 10,000x, becomes 10,000x squared divided by 2. And our final term becomes minus 25,000x cubed divided by 3. Now we substitute our 0.6 value into the x terms here, and then subtract the same equation but where x is equal to 0. This means that the second part of this equation is equal to 0, so we're not subtracting anything. And when we sum up these terms here, the work that we get is 9,000 joules or 9.00 kilojoules to 3 significant figures. So the expanding gases supply approximately 9,000 joules of energy to the bullet over a distance of 0.600 meters. Now if we go back to the work kinetic energy theorem, we can use this information to estimate the speed of the bullet as it leaves the barrel. And some of you might already know that the longer this barrel is, the faster the bullet can potentially be when it leaves the barrel. So from here, it's really simple to find the speed of this projectile as it leaves the barrel. So the work done is the kinetic energy gained by the projectile. So we can rearrange this, and we want to make the velocity the subject of the equation, and we end up with the velocity is equal to the square root of 2 multiplied by the work done on the projectile by the expanding gases divided by the mass of the projectile. And we can substitute in our values here, making sure that we're using SI units, and we get an estimated velocity of 424 meters per second to 3 significant figures.